Alright guys, hey, this is our last video for chapter 9. Remember, this is on periodic trends. This is going to be real quick. You will need your periodic table out for it. Remember, if at any time you are confused or need to go back, just rewind or pause it so you can make sure you get everything down. Also remember, you only have to write down the red and then whatever I write on the screen. So, first thing we're going to focus on is Zeph, or effective nuclear charge. Now, that is the nuclear charge that is felt by an electron. Remember, electrons are on the outside, and really we're talking about valence electrons. And as we go across the periodic, as we go across the periodic table from left to right, Zeph increases. It also increases going up. Now, I know that Zeph is not one of the ones that you wrote on your periodic table project, but it is an important one. It's just how strong of a pull the electrons have from the nucleus. Okay, this is really the reason why most of the other ones happen, most of the other trends. The next trend is going to be atomic size. Now, it wants you to write these bullet points down. Y'all, all you really need to write down are the arrows. So there are two sets of arrows. There's ones that point left and down, and there's ones that point up and right. Atomic radius or size, those are used interchangeably, are left and down. Okay. It is because Zeph is pull, so as you go left, pull is less. Really, as you go right, pull is more. So at the beginning of a column, or at the beginning of the row, pull is not as strong. So because of that, they're kind of puffed out some, the atoms. Once you go to the right, they get smaller because they've got more pull, and they're getting smaller towards the nucleus. As we go down the column, we do know they increase. There's going to be a picture on the next slide, but it is because our energy levels are increasing, so we are literally gaining rings. Like on ring 1 or on row 1, we're there. Here we're on row 2, we're there. On row 3, we're just gaining rings. Okay, so they have to get larger as we go down because they're gaining rings in their atom, and so they have to get larger. Here you can see as we go down that first column, the alkali metals, they get larger, but they do that in every column. It's because they're gaining rings. And as we go across, they do decrease in size because of the pull. But the main arrows you need for atomic radius or atomic size are these, because I want y'all to draw increasing arrows. I do not like these decreasing arrows. Okay, I don't like them. I prefer you not to use them. All right, so here we are just comparing the elements. So between carbon and oxygen, carbon is closer to the left side of the periodic table. It has less pull or less Zeph, so it is our larger atom. Lithium and potassium. Potassium is lower. It's got 4 rings versus 2, so it is larger. Aluminum and carbon. Aluminum has 3 rings, carbon only has 2, so that's our larger one. You know, selenium and iodide, it'll be in the picture, but this is a we cannot tell situation because, so again, here's our overall arrows. This is the general direction, and because selenium and iodine are the opposite direction, and you see here, if I draw the arrow this way, they are the opposite direction, so we just say we cannot tell. I will not ask any like that on the test or on a quiz, okay? All right. There are some if you would like to try them. There are some in mastering, so if you don't want to try them, it's fine. We're going to keep going. All right, next is ionization energy. Now, ionization energy arrows are opposite of atomic radius arrows. So if you want to go ahead and draw the arrows, they're like this. They look like the Zeph arrows. Okay, they increase as you go to the right, and they increase as you go up to the top. So the highest ionization energy on the periodic table is helium. Again, they like those decreasing arrows. I do not like those. I'm good with this bottom one, but the other side looks like this. Again, this is how we draw them. All right. Oh, I would like you to know what ionization energy means. That is, so let's go ahead and write down the definition. Ionization energy is the energy required to remove one electron from an atom. Or from an ion. It may have already lost one. Okay. That is what ionization energy is. So, if you think about it, helium is the highest. Helium has a full shell, which means it does not want to lose an electron because it's stable. It also does not want to lose one because it only has two. They are very close to the nucleus. They are held very, very tight. Something like francium, though, or any of the alkali metals, they want to lose an electron because they're alkali metals and they have a +1 charge. So because of that, they have very low ionization energies because they don't want to lose it. Or they do want to lose it, so it's easy to pull it off. It is the energy required to pull it off. The more energy it takes, the higher the ionization energy. All right, so let's look at comparing. We've got magnesium and phosphorus. So obviously phosphorus is closer to helium. We're just looking for what element is closer to that anchor element. Arsenic and antimony. So arsenic is higher, so arsenic is our answer. Silicon and nitrogen. This is a diagonal, but nitrogen is closer because the diagonal points the same direction. And oxygen and chlorine is we can't tell the difference because it's that weird diagonal. All right, so if you need help, let us know. And by us, send me a message, please. Next is metallic character. Now, this was not one that we did on our periodic table project, but it is the same arrows as atomic radius. All right, so metals we know tend to lose their electrons and nonmetals gain them. And so metals obviously should have more metallic character than a nonmetal. Okay. So again, don't like those decreasing arrows. Please draw the arrows from before. We're looking for the element closest to francium because that's our furthest down to the left element. So we've got tin and tellurium. Tin is a metal, tellurium is a metalloid, so tin is more metallic. Silicon and tin. Silicon is a metalloid, tin is a metal, so tin is our more metallic character. Bromine and tellurium. Tellurium is a metalloid, so it has more metallic character than our halogen. Then we've got selenium and iodide. Okay, this is we can't tell because they're that opposite diagonal. Again, I'm not asking any of the opposite diagonals on the test day. Okay, more practice if you need it. Y'all, and that's it. So you should be able to finish mastering by this point. If you have any questions, please reach out. Y'all have a great day.